So last time I finished in the middle of giving moments of inertia for the four simple shapes. So mass moments of inertia for four simple shapes. Continued. So we did a slender rod, we did a rectangular plate, a thin rectangular plate. The next one is a thin disc. Okay, and those are the axes that we're going to consider rotations around. So the x-axis, the y-axis, and the z-axis. The moment of inertia about, okay, so again, just like with the thin rectangular plate, you have to consider whether this thing is rotating like a blade, like a rolling wheel, or whether it's rotating like a paddle or like flipping a coin, okay? That's going to determine which one of these you use. In this case, about the z-axis, is that like a blade or a paddle? That's the blade, so that one has its own formula, and it's mr squared over 2. And the other two are both the same. Those are both flipping end over end, like a paddle. So the moment of inertia about x is equal to the moment of inertia about y, which is equal to mr squared over 4. So it rotates more easily like a wheel or a blade than it does like a paddle or a flipped coin. No, that's not true. It's the opposite. It rotates more easily going flipping end over end. And then the next one is a sphere. This one, all of the axes are the same. Rotations are the same no matter what. So the moment of inertia about x is the same as the moment of inertia about y, is the same as the moment of inertia about z, and it's equal to 2/5 mr squared. Later we'll do a careful calculation of this, but the difference between, so if you had a disk rolling, the moment of inertia that matters would be mr squared over 2. If you had a sphere rolling, the relevant moment of inertia would be 2/5 mr squared, right? So it's, well, if they had the same moment of inertia, this would be 2.5 over 5 mr squared. And that is the final reason, underneath a bunch of other stuff, why if you roll a disk so start a disk and a sphere at the top of an incline and roll them down together, the sphere will get down to the bottom faster. It has a lower moment of inertia than the disk rolling like a wheel. All right, so notice that for all these formulas, are for moments of inertia about the center of mass. But there are a lot of, I guess there are three different reasons why you would sometimes want to know the moment of inertia about another point other than the center of mass. So how do we represent moment of inertia about other points? And the answer, there's an easy formula for it. It's called the parallel axis theorem. So say this is the body of interest. This is the center of mass of the body. So if you can calculate the moment of inertia about an axis going through the center of mass, and you want to calculate the moment of inertia about a parallel axis that doesn't go through the center of mass, so I'll call this axis C because it goes through the center of mass. I'll call this one A. There's a distance D between them that has to be perpendicular to those two. It's the shortest distance. So if C goes through the center of mass, and A and C are parallel, then the parallel axis theorem says the moment of inertia about A is equal to the moment of inertia about C plus md squared. M is the mass of the body. D is the distance between the two axes. So let me show how this comes up. Let's say that we have a T shape. Is that what I want to do? Yeah, let's do it. Okay, so let's say that this distance is 1 meter. This distance is 1 meter. Let's say all the thicknesses are 0.1 meter. And let's say that we want to calculate the angular acceleration of this object. And let's say that the mass density So let's say the mass is given by 50 kilograms per meter. Okay. So it's like a density given in terms of the length. So how would we calculate that? Well, we need to use the rotational equation to do that, which says that the sum of the moments about A is equal to the moment of inertia about A times the angular acceleration. And A is either a fixed point in an inertial coordinate system or the center of mass. Any case where there's a fixed point, we want to use that as the about point. Is there a fixed point in this case? Yes, so we want to make the pin down there our about point. Okay, so let's break this shape up into the top and the bottom piece. The top piece, okay, each of these two pieces has a mass of 100 kilograms. And, okay, we also have to think about which way are these rectangular shapes rotating. Are they rotating like paddles or are they rotating like blades? That's right. Yep. That's right. So so we want to use a moment of inertia about the center of mass of each shape is equal to 1/12 times the mass times 1 squared plus 0.1 squared. Okay, for each of these. So I'll make this point A. So for rectangle 1, the moment of inertia about A is equal to, oh, can someone calculate what this is? 100 times 1.01 divided by 12. 101 divided by 12. Okay. And that's kilograms per meter squared. No, kilogram times meter squared. Okay, so the moment of inertia about this point A now that we want is equal to 8.417 plus md squared. So the mass is 100. What's the distance from the center of mass of rectangle 1 to the point A that we want? That would be 1 meter plus another 0.05. So 1.05 squared. And so what do you get there? 0.667. Okay? So that's for rectangle 1, and notice that by far the bigger part of this moment of inertia, rather than coming from the shape, just came from how far it is from the axis that we're considering. So that parallel axis theorem contribution can be huge. And then for rectangle 2, the moment of inertia about A is, so the contribution of the shape is the same, but this time we have 100 kilograms times this one. What's that distance, D? This is the 0.5 squared. And so 8.417 plus 25, what's that equal to? 33.417. And now we can add those because we have the moments of inertia for both of them about the same axis. You can't add them until you've calculated that about the same axis. So the total moment of inertia about A is 118.667 plus 33.417. What do you get? Okay, and so then now the rotational Newton's second law says add up all the moments about A. That's equal to 152.083 times the angular acceleration. And once you calculate the moments, you can calculate that. Okay. So, you know, I said it's really easy to mix up this mass moment of inertia that we do in this class and the area moment of inertia that you do in D-form. This is another case where confusion comes in. They both have a parallel axis theorem, and they look almost just the same. The area moment of inertia, the parallel axis theorem term is you add on the area times the distance squared instead of adding on the mass times the distance squared. Okay, so again, it's just making it, all of these similarities are just making it easier to confuse those two things. Okay, so now we've defined the acceleration of the center of mass, the moment of inertia about A. Now I'm going to give you a set of, well, I guess let me do a definition of moment, but the calculation of a moment is going to come up in the steps I'm going to give you for solving these problems. The last thing we need, this is the last thing we need, believe me, is the moment of a force about a point. The idea is that the tendency of a load, or the tendency of a force, to cause a rotation depends on the force. But it also depends on the perpendicular distance from the force to the axis of rotation. So for example, if you're trying to turn a bolt and you have this wrench, that's an ugly wrench. It looks like a snake eating that bolt. Okay, so say that you're capable of applying 500 newtons to that wrench. Where are you going to apply it? You know, like if you want to apply it at the end. You don't want to sit here. You know, that's not going to do anything. It might shear the bolt off, and then you're done for the day at least. But so what matters is this force, but also this perpendicular distance, and I'm going to call it rho. And by perpendicular, I mean perpendicular to that force. Okay. And so in 3 dimensions, if this is the object, and the force is like that. What? Go up. Okay. And let's say that your about point is here. Then define a row vector that goes from A to F. So you could do all the geometry, all the trigonometry to figure out a perpendicular distance, but the cross product will do it for you. So let's just do that. We'll call this vector rho. We'll call this vector F, the force vector. And then the moment about A produced by F is equal to rho cross F. Okay, so that's the definition. It works in 2D, 3D. It's the only definition you need. And, you know, I said the Newton's second law and the rotational equation, they're analogs of each other. So obviously, in the rotational equation, the moment is the sort of rotational version of force. That's the load. Okay, so let me give you a set of steps that'll work for rigid body kinetics problems. Okay, so the first thing you have to do when you're going to use the rotational equation is figure out, is it rotating about a fixed point or not? Is it rotating about a fixed point? If yes, the fixed point is the about point. If there's no fixed point, then make the center of mass the about point. There are still going to be times when, so if you have an object that doesn't have a fixed point, so your about point is going to be the center of mass, there are still times that you need to use the parallel axis theorem. Can you think of how that would come up? I'm not leaving till someone comes up with a good. Okay, all right. I get that was a dumb idea. But if you have a shape that is made up of like three simple shapes, then you're going to add up the moments of inertia of those simple shapes to get the total one. But the center of mass of the built-up shape isn't in the same place as any one of those three individual centers of mass. And so you have to first calculate where the center of mass of the combined thing is, and then calculate the moment of inertia of each individual piece about that combined center of mass. Okay. Okay, the second step is calculate the moment of inertia about the about point. The third step is free body diagram. And the fourth step is the pancake table. So the pancake table works like this. The mnemonic device is pancake, artists, row, for, marzipan. It's like marzipan is like fancy frosting that no one's ever used on a pancake. What? I've never heard of that. Is that? It's like a small rodent.
No, it's a talking.
Oh. Okay, so pancake, artists, row. See, that's the Greek letter rho. That's sort of a clever one. For marzipan. This one is, you just enter the coordinates where that force is applied. A is the coordinates of the about point. Rho is P minus A. F is the force vector. And then the moment is rho cross F. So there's no new information in this table. It's just a nice way to organize your information. Be sure you don't miss anything. Be sure you get your row vector pointing in the correct direction, that kind of thing. But this is a table where you have a row for the first force, a row for the second force. You go all the way down. I'll show some examples of how to use this. And then the fifth one, normally you're going to be able to skip this step if your about point is fixed in the coordinate system. But the last step is use Newton's second law. Oh, wait. Why did I do it in that order? All right. This isn't the last step. There's one more after this. Newton's second law. Add up all the forces. Those have to be equal to the mass times the acceleration vector of the center of mass. And the nice thing, a nice thing about setting up this table is you can just go straight down this column, take each one of those forces, and the set of forces on the left side of Newton's second law just comes straight from this column. Okay, so you have a list of 5 forces or whatever. They just go right over here. And then the last step, number 6, is use the rotational equation. That says the sum of the moments about A is equal to the mass moment of inertia about A times the angular acceleration. And just like you got your forces directly from this column here, you can take your moments directly from the last column and put them in here. Then, if you need to calculate the acceleration of a point on the body, you can use the fact that the acceleration of that point relative to your about point is equal to, it's the watermelon equation. So alpha cross r plus omega cross quantity omega cross r. That last one is going to come up a lot when we start doing linkages. Okay, let's do a simple example. Yeah. Let's not do a simple example. Let's just do the quiz. Then you'll have time for a change. So on Monday, I'll go through examples, and we'll get plenty used to this.